Let's begin then. So just to explain what this is part of a seminar series that we do occasionally called the Happy Scientist Seminar Series, which is designed to educate us really about tools and techniques that will make us more productive and therefore happier as scientists. So chief responsibility for our happiness of late has been on George's shoulders, and he's been very up to the task. And today he's going to describe how to make us happy through parallel computing. So George, it's all yours.
Okay, thank you, Paul. So before we start, let me give you a web address I just shared on the chat. Today we're going to be relying heavily on a website that I created for this. Now let me share screen. Okay, so for those of you who don't know me, my name is George Vega. I'm a research programmer at Biostats. I recently got my PhD in Biostats with Paul as my chair and Duncan part of my committee. And today I'm going to tell you a little bit about how to work with a USC cluster, essentially, and how to use slurmR, which is an R package that we developed actually, it's a year and a half ago, maybe 2 years ago, that makes it easier to interact with Slurm clusters in general, okay? So this is the website I was telling you about. Here I have all the materials. You can go there, download it. I'm just going to post it again because I realized some time ago that if you get late to a Zoom meeting, you might not be able to see what was previously on the chat, but you can go there, okay? And furthermore, if you click on that link there, right here, we actually have a website, like an actual website for the entire thing. So this is the GitHub repository, and I'm going to share also that web address here. Give me 1 second. Everything it's the same thing. So, but if you go there, it will open this window, which is a bit nicer. So this is the website for the workshop, and it's going to have two main parts. The first, I'm just going to give you the fundamentals in which we are essentially going to try to do a hello world using slurmR. And in the second, I'm going to introduce you to the slurmR package. Okay, so give you some more practical examples, simulating pi, which is something that I've done many times. And before we continue, also let me tell you a little about the feature scientists, the feature happy scientists. We usually have someone here that we would like to discuss. And in this case, we have Lynn Conway. She's a computer scientist who is famous for inventing the generalized dynamic instruction handling. And the bottom line is that this thing that she invented is the fact that this is a key development for parallel computing now these days. So which is why it's very relevant for this talk today. And another interesting thing about her is that she used to work for IBM, and I think it was in 1960s or something. She was fired by IBM because she's a transgender person. But later in 2020, IBM apologized to her, and they actually gave him a Lifetime Achievement Award. So she has a very interesting story. So I invite you to take a look at her. Okay, so let me start. The first part. And if you have any questions, just let me know. I hopefully will go through the first part in roughly 20 minutes or so. It should be quick. I apologize in advance because, again, so this is designed to last like 2 hours or something like that, but we don't have that much time. So I'll just give you a glimpse. And if you have, I put a lot of links and other stuff around. So if you have a question more profound, you can send me an email if you want. We can discuss that later on. Okay.
George, just a quick question about the follow along package. Do you recommend cloning or forking? Because in another word, are you going to make modifications to this after perhaps, or is this kind of like done?
I actually, this is the second time I do this. So if you take a look at the home page here, it actually said so. This takes you to back in time in 2019. So if you fork it, you won't be able to get a updated version. I will keep updating this through time. So
okay.
Okay, so
Thank you.
Any other question? You're welcome. Any other question? No? Okay, so for those of you who are not familiar with this, HPC recently went through a lot of changes. We used to have a single cluster, essentially. Now we have actually 2 clusters who have different approaches. A cluster means just a set of computation nodes, okay? And we have the discovery cluster and the Endeavor Condo cluster. The discovery cluster is the main queue in the sense that people, anyone in USC, students, staff, faculty can have access to the discovery cluster regardless of whether you put some money on it or not. And as soon as you apply for your HPC account, which you can do if you go to CARC, that's the website, carc.usc.edu, you can access all of these resources for free. Okay, and the way that this is structured is that we do have these 2 set of clusters. We have a storage file system, which is composed of actually 4 main storage spaces. We have the home directory, which is where you get in once you log into the HPC cluster. We have the various projects in which I think by default, once you get an account, you get 5 terabytes of space. And we have the Scratch and Scratch 2 file systems, which are used to store temporary files. And lastly, we do have the login nodes, the head nodes. And we have here, we have a set of login nodes for the discovery cluster. We have a set of login nodes for data transfer, which is mostly used if you want to upload or download some data to and from the HPC cluster. And we have the Endeavor login nodes. Okay, so this is the main phase of it. This is just for management, this set of nodes. This is for storage, and all the computation or parallel computing or whatever you're running is going to be happening within these clusters, not in these nodes, but in these nodes. Okay, please let me know if you have a question.
So so for large, you can store a lot of data on the storage nodes in a home folder or a project folder, or
in the project folder, right?
Yeah.
Because that's a good point. In the home folder, we only have 100 gigabytes of storage space, which can be actually you can eat up very quickly. So I do not recommend use the home directory for storing big data. You can use the home directory for keeping your scripts, maybe a few packages, but not more than that. Okay. And of course, I forgot to mention, all of the jobs are actually scheduled, like organized by Slurm. Okay. Okay, so let's start. This is the hello world. I will be switching back and forth from a command line to here. Okay. So what we're going to be doing is essentially just using R script to print a message, but submitting this to the compute nodes using Slurm. Okay. So the first thing that we need to know is that we will need to take this R script, move it to HPC. Okay, so we have to copy it. You can download it. Did I put it somewhere? Oh, I did not put it to download it from anywhere. So I'll show you how. And then once we copy it to HPC, we need to log in. Okay. And once we are in, we can actually submit the job using sbatch. Okay, this is a batch script. This is a Slurm script that has this structure. And I'm going to copy this over the chat if you want to copy it right away. Okay. And let me explain you what do we have here. So the Slurm scripts are the main ones that we use to specify the structure of a job that is going to be submitted to Slurm. Okay. So first we have the shebang line. You can get more info there. I put a link. The only thing that you need to know about it is that you need to put it in all of your Slurm scripts. Then if you want to specify an option to Slurm, meaning that if you want to specify the number of processors that you want to use, number of memory you want to allocate, the time that you want to use, etc., you can specify that using the hash sbatch tag. For example, in this case, I'm telling Slurm that I wanted to use the std in output out an error to this file here. So once whatever message it's printed is going to be printed out to this file. And finally, these two lines are the key ones, right? The first one loads R, okay? USC, it's a special model in R. So it used to be the case for those of you who had a chance to work with the previous version of HPC. If you wanted to load a version of R, you will need to go and type something like source and go to some directory to load a particular version of R. Now, instead of that, we're using the L mode software that allows us to do this kind of like dynamically in an easier way. So when you type module load USC and R, it's going to automatically load the latest version of R installed on HPC. You can see more details about it here. And finally, since we now have R available, because you have to like load R in the compute node, then we can call an R script like I'm doing right here. I'm essentially just, this is an R expression. That's how you can do like computations on the fly with R. And I'm just pasting hello world from node, and I'm getting this slurmD node name environment variable. That's how you get environment variables in R. That way, essentially tell me the name of the node in which I'm currently doing this right now. Okay. So just for you to get an idea, let me just show you this how it looks like if I just do that on my computer without logging into HPC. If I type R script. Okay, if I type R script expression and then I type something like 1 + 1, okay, this is just running R and executing that expression and returns. If I type R script expression, paste hello world, it does exactly that, right? See, so this is just a way to communicate with R. I don't know, this time. See, so that's what we're doing. It's nothing fancy. We're not doing simulations or anything. This is just a simple hello world from R, okay? And sorry, I forgot to include the link to that file. Let me go back, because the next thing that now that we have this, we need to copy this to HPC. And let me show you how to do it. Let me, and give you the link to that file. I forgot to include that. Sorry. So if you want, you can just, I'm going to copy this address on the chat. I will update the tutorial online so it can include this link directly on the tutorial. But if you go there, you can click to this link that I just shared with you, and it will to download this file so you can then upload it to HPC. Okay. Okay, so as I said, the next step is that we need to copy this to HPC. A way to do that is using Secure Copy Protocol, SCP, which is the standard way of doing it. But I recommend you to take a look at different GUIs that are out there to like communicate with HPC. So instead of you using command line to copy and move files around, I think that I use, for example, is FileZilla, which for me is more convenient. I find it like more useful, easier to use. And I put the link in MISC. So if you want to take a look at it, how to set it up by yourself, you can go there and actually in CARC, they have which is the website of USC's HPC. They have a very nice tutorial about how to set up different GUIs to move data around to and from HPC. Okay. Okay, so let's imagining that you already got the data. Okay, so in my case, for example, I do have the hello world slurm here, right? This is the file that I want to copy over to HPC. And the way to do it, as I'm showing up here, I'm going to copy this also to the chat window, so you can guys have it easier. Okay, you have to change this, by the way. Sorry. Oops. There you go. The way to do this is essentially, I'm just going to copy this, and I'm going to explain you step by step what am I doing. Okay, so first I'm just calling the command here to copy it. Then I do have the hello world that's Slurm script here. So I'm moving essentially. I'm telling this function to go take this file, okay, connect to HPC transfer1 at usc.edu using vegayon as my username, and copy this file to home1 vegayon. So of course you will need to replace vegayon with whatever your USC net ID is, and the USC net ID is whatever comes before your @usc.edu email. Okay, so once I do that, once you do this, you should get all the prompts to enter your password. In my case, I skip the password because I have a special setting that allows me to don't type the password over and over again. But it will prompt me the dual authentication, which I'm pretty sure you are familiar with. Okay, so once I do that, I go to my phone now, and I approve. It just moved the file to USC's HPC, right? To this location in my case. Any questions so far? So all that we're doing right now is just, again, I have this R script that is going to, sorry, this Slurm script that is just a hello world to be run on USC's HPC, which I took and I copied to my home directory on HPC. Okay, that's all that we've done so far. Okay, so now the next step, now that we have that, is to actually log into HPC and then later on submit this job. Okay, so what I'm going to be doing next is just logging in. And the way to do that, if you have Windows, you can do it through the PuTTY client. I'm going to copy this web address here. You can go there and download the program. It's very easy to use. Okay. And if you don't have Windows, you can always use, if you're running on Linux or Mac, you can just use SSH directly, right? So in my case, the way I do it is I just type SSH, my username, my USC net ID actually, and I'm going to be logging to the Endeavor, actually, no, just to the Discovery cluster. Okay, just like that. Again, it will prompt you to, it will ask you to enter the password. In my case, I skipped that because I have a special thing that allows me to skip doing that. But it will ask me to use the login duo, the duo push notification. So I am going to be doing that. Okay. And now we're in. Okay, see? So now, as you can see, I'm in the home1 directory, vegayon, and if you take a look at it, if I take a look at this, you will see that I just have a file, oops, right here, the hello world, that's Slurm file that I just moved a couple of minutes ago. It reflects here, see? So I can print it on screen using cat. I do that, see? So it's right here. And we are essentially pretty much ready to submit this job to Slurm, okay? So how do we do that? Well, the next step is just use sbatch. Sbatch is the command line tool from Slurm that allows you to submit batch jobs, okay? So if I go now and type sbatch 00 hello world, that's Slurm, okay? And I type enter, it submitted a job. The SQ function, the SQ command line program allows you to query what's going on and what's on the queue on Slurm. And in this case, I'm using the U flag here to specify that I just want to see what's going on in the case of the user vegayon, which is myself. As you can see, it's empty. There's nothing going on. And that's because this job in particular happens very quickly. Okay, so if I just list it out, I'm just going to list these files. I have here the hello world Slurm file that I just copied a few minutes ago, but now I have this other new file here that was just created, hello world.out. If you recall, I have here amongst the options, I set up that the output should be called 00 hello world out, okay? Which is what we are seeing here. And if I print this on screen, this is the result. Okay, so in other words, what just happened is that after I submitted the job to Slurm, Slurm allocated node, which is just a computer, let's say, D0540, and allowed me to make and executed the R script right there. And so when it ran this line of code, this line here, it took the system variable slurmR node name, which had this variable, and then printed out as a message, hello from node D0540. Okay. Any questions so far? No? Okay. So that's pretty much it with that. Lastly, before jumping into the second part, I think that I usually do some that I will do sometimes is that if I, for example, let's imagine that you just run a large job and you want to inspect some very large data sets that you cannot open in your computer, right? You would need, I don't know, like 40 gigs of memory or something like that, which might be too much for your RAM to run it. So a way to deal with that is using an interactive session. And to do that, we can also request Slurm to get an interactive session. So let me show you this line here. And the way to do it, for example, in this case, what I will be asking here is I will be asking Slurm to provide me a node, okay, in which I will have a single task. I want to use 8 cores or 8 CPUs, 2 gigabytes per core. So in this case, it's going to request 16 gigabytes for 1 hour. Okay. So when I type this, if you copy and paste this on your command line once you are on HPC, sorry. If I do this, oops, yeah, that's the wrong task. I should have checked that. That's meant per CPU, not per task. Sorry. Let me correct that. Again, that's another thing that I will be changing for the next version. Okay. As you can see now, Slurm just allocated a node for me, and it allocated this node. So as you can see now, it's different, right? So before, when I log in, it used to say Vega-Ion Discovery 1, but now instead it says Vega-Ion at D1124, which means that we are in node D1124. This is a compute node. And if I wanted to use R, I will just need to type module load USC R. Okay, and now I can actually go and use R interactively. See? And for example, if as I mentioned, I requested, I said how many cores, 8 CPUs. So if I query, I actually right now in this machine there are 24 cores, but I got 8 allocated to me, so I can actually use 8 cores and without worrying. Okay, so this is the way to essentially do computations. If you want to, again, if you want to like work with some data set on HPC, you should not do that on the head node. You should request resources using salloc, as I just did. Okay. Okay, so that was the first part. Now let's go to the second part. Any questions so far?
Yeah. What is the difference between a core and a CPU?
That's a very good question. So actually, there's many differences in general. So actually, CPU, central processing unit, we usually with core we think about them similarly, but the key thing in high performance computing is that essentially you will have you may have many, you may have a core, but that core may have maybe multi-threaded. Okay, so actually, let me show you very quickly. Slurm actually has like a very nice diagram showing all of this. By the way, I always check the help files in Slurm. So let me see, where is it? Okay. So they have here a section in which they describe in detail, because you can personalize Slurm in various ways. So here it is. So you have the core, right, which is a private set of execution units, a single core, but then each core may be multi-threaded. That's usually with Intel. But then cores themselves are grouped in sockets. Okay, so that's kind of like the general structure. So let me put this in the chat if you want to take more a detailed look onto this. Here you go. But usually you should care about CPUs, right? When we're dealing with Slurm, the way to specify things is specifying using CPUs. Okay, not nodes directly, but that's something that I can talk about later. Okay. Any other
George,
questions?
can I be your TA for a second? Do you have a question in the chat window from Kevin, who asks, how do I decide how many nodes, CPUs, and memory I should request if I want my programs to run as fast as possible?
Right, that's a great question. So the thing that we need to clarify is that Slurm itself does not turn things into parallel computing out of the box, right? So it just manages resources and allocates space. That said, when you're dealing, for example, with R, you need to take care of how many cores you're using. So for example, as I will show in the examples that we have now, when you are doing multi-core computing, you have to be explicit with that in R. And based on that, you can tell Slurm how much resources you want. Because in other words, for example, if you write an R script and then you submit it to Slurm and you say, I don't know, and CPUs per task 24, that does not mean that automatically it's going to be using 24 cores out of the box. Because if your R script it was written to be executed serially in a serial fashion, it won't be running parallel computing right away. Slurm will allocate the 24 cores that you requested, but your program will be essentially just using a single core when you execute it, right? So that's the main thing. And I guess a rule of thumb, I don't know, like 20 cores is something reasonable. But instead of that, as I will show you later on, instead of thinking about cores that way, the way that I tend to think about HPC and Slurm, it's using job arrays, which is something that I have an example here, which essentially allows you to request, I don't know, hundreds of cores at the same time. But I will show you how that works, okay? And yeah, Paul, please, if you have a question, just let me know if anyone has a question or something. Okay, so as I mentioned earlier, we are going to be simulating pi once more. The bottom line idea is that we want to approximate pi using Monte Carlo simulations, which is an ideal example, right? Simulations can be embarrassingly parallelizable. And the way to do that is that we take a unit square and we randomly throw dots around that unit square. And the probability and if we use the probability, if we try to approximate the probability that a square can fall, a point can fall, dot can fall within this unit circle, then we can actually approximate pi based on the area of the circle. Okay, so here's the math. If you want to take a look at it, I won't go into detail, but it's very simple. So the only thing that we need to do is that just randomly simulate a bunch of points within the unit square, and then see what proportion of them fall within the unit circle, and with that we can then approximate pi. Okay. So that's what we're going to be doing. And again, so I just went through this. This is how to submit jobs to Slurm. In this case, this is the script, an example script. Okay.
George, by the way, for people using Endeavor, I think you need an extra line in there to run the script to
That's right.
specify the partition.
That's right. If you're using Endeavor, that means that you have pre-allocated resources for that. So in the case of Biostats, most of the folks there have access to the county cluster. So then you will need to use your account number, which let me show you. You can get your account number by just typing, if you type my quota, once you're logging on HPC, it will show you how much space left you have in all of the projects that you are assigned to, but it actually shows you also the group numbers and group IDs. So for example, I have other Jim's group. This is the county group. So if you are using the Endeavor cluster, if you want to submit a job, you have to specify the account, which will be the county 251, and the partition, which is the county partition. But I can tell you more about that later if we have enough time. Okay. For now, for the general public, if you're using the discovery cluster, you don't need to specify any of that. You can specify the account if you want, but it will take one of the ones that you have by default. Okay. So there's no need of doing that right away. Okay. So here's the job that we're going to be submitting. Okay. So if you click there, I'm going to just copy and paste the link to it so you can get it for you right away. This is the R script that we're going to be running on HPC. This is a single job, single core. It might be, imagine that is a simulation that takes a long time, right? So you want to run it on HPC instead of your computer, and you can do it. And it's very simple, okay? So here I have a number of simulations. These are one of the parameters that I have. A number of samples. I will tell you about it later. And I have this function SimPy, which is very simple again. So the only thing that it does is that it just samples squares from a unit, points from a unit square, I guess, and then it computes the probability of falling within the circle and returns an approximation of pi. So if we actually run this, let me show you. I'll just copy and paste this and run it on my session here. If I'm running R, okay, and if I just copy this function here, SimPy, I don't know, I want to simulate 1,000,000 points. Oops, I need to end. If I simulate 1,000,000 points, it gets an approximation of pi. See, so that's all that it's doing, a random approximation of pi. That's all that it returns. Okay. So that's what we are going to be doing. And together with this R script, we do have the Slurm script, which looks very much like the one that I just showed you earlier on, right? So we have the shebang. In this case, I'm adding a name to the script. Okay. It's going to be called isApply. And it's going to last, and I told Slurm that I don't expect this to last longer than 10 minutes. And this is important because this is essentially you're giving Slurm an estimate of how much time do you think it's going to take for this computation to be finished. Okay. So with this in hand, I already have all this copied on my session. So let me just go there. If you see, I do have this example here. I have the R script that I just mentioned, right? And I have the Slurm script right here. This is the Slurm script. Okay. To submit it again, I just need to go there and type sbatch 01 isApply Slurm. Right?
I can't see what you're typing. It's too low on my screen.
Sorry, what?
Yeah, that's better.
That's better? Okay.
Yeah, but I didn't see it before. I couldn't see it.
It was to the bottom. Okay.
Yeah.
Okay. I'll keep a mind on that. So we just go sbatch and then the name of the batch script that we want to submit. It's done. I submitted it. I can check out the time. I can see if it's okay. Again, this was pretty fast, so that's why I don't see anything. But just for fun, if you want, if you type SQ just like that, you can take a look at what's going on HPC right now. In this cluster, as you can see, there's someone who is using a ton of resources. In particular, this person is using, I don't know who this user is, but he's using a job array. He's requesting a few hundred, maybe 100 cores. That's something that you can do on HPC. See, you can see what's going on. And furthermore, if you type sinfo, you can take a look, get a glimpse of the, let's say, the resources available on the cluster. Okay, so we have a bunch of partitions. We have the debug partition in which 5 nodes are idle, and then with a star, which I don't know what it means, and then we have other five nodes here. We have the main queue here, which has a bunch of nodes, and this is important. We do have 3 large nodes that can be used if you have like very large data sets. In particular, the large mem nodes have, I think it's 1 terabyte of RAM. So if you have a very big data set that you would like to process, you should be using the large mem partition. Or if you have something that lasts very long, you have like I don't know, a computation that lasts like a week or so, you can use the 1 week partition. See, so we have 35 idle nodes that are named like that. Okay. So let's see the result.
How do you specifically request access to those partitions?
That's a very good question. So if I wanted to, for example, use the large mem partition, you will go and type -- partition large mem, just like that.
Cool.
And if, for example, if you were on the discovery on the Endeavor cluster, and you want to submit this to the county condo, you will do something like account. I don't remember the account number, but it's something like, I don't know, the county 124. I don't remember exactly the numbers, but then I will type partition county, and this will submit a job to the county partition.
George, we have another question. Sorry, are you finished, Abigail?
Yes, thanks.
Another question from Jingying asking how to find out the maximum job CPU or memory you can request on any particular queue, I guess.
Yeah, so HPC, you can go to the website. I think I put all those in the MISC link on the website there. But again, so if you are working with R and you want to use multiple CPUs using the regular R tools, which are not, meaning that it's not using the slurmR package, I think it's like up to 20 cores at the same time. If you are using a single node, you cannot request more than that. But if you are using job arrays using the slurmR package, for example, I have requested up to 300 CPUs using the slurmR package. Okay, any other question? No? Okay, so what we just did, again, I have this R script here that I already have loaded on my HPC account, and I have this Slurm script that I also have loaded, and I just submitted it using the sbatch as you saw earlier. I just type sbatch 01 is apply slurmR, and if we take a look at it, let's see. Here I'm just listing the files here, ordered by time. As we can see here, we have this RDS file here that was generated. Oh, but sorry, give me 1 second. I forgot to update this. So this is one tip. Sorry. Instead of using SCP and FileZilla and everything else, another way that method that I use to upload files and scripts to Slurm is actually to HPC is using Git. So I recommend you to set that up on your own. We will have a Happy Scientist seminar on Git in February 18th, I believe. So, okay, so let me just repeat this. I'm going to resubmit this because I forgot to add something. Okay, so I submitted this batch job here. And if we list it all, as you can see here now, what's going on? SQ. Nothing was submitted yet. Okay, no, but that's fine. Oh, I didn't. Okay, I was looking for a name. Sorry. In this case, since as a different from the previous example, if you remember in the first part, when I submitted the jobs in the bash script, I actually specified the name of the output here, right, with sbatch. And the example which I just executed, I did not do that. Okay, if you take a look at the batch script here, where is it? Right here. It does not specify the output file name. Okay, so by default, when that happens, what Slurm does is that it just puts the prefix Slurm and then the name of the job, the number of the job ID. Okay, so if I print this out, this is just a message that is pre-specified here. So this is, as you can see here in this R script, once it's done simulating, I ask it to print out the average value of pi that it's simulated, and it's right here. See? And it also saved an R file that's called 0001 sapply.rds, which is the file that you can see right here. This is the file that was just generated. Okay. Any questions so far? Okay, again, just to repeat, this is fairly simple. Two files, right? I have this R script that I want to run. This could be your simulation, your model. And I have this Slurm bash file that I want to, the Slurm script in which I'm specifying the instructions, right? So this is the same structure as before. The only difference is that I added a job name here and a time that I believe will, how long it will last. I loaded the modules, you see R, and then run R script vanilla, and then the name of the R script that I want to execute. And that's it, and it worked, just like that, okay? So now the next example deals with when you're trying to use multiple CPUs, multiple cores, okay? Parallel computing, in other words, right? So in this case, this is very much the same thing that we had before, okay? It's very similar, the same R script. Again, we're just simulating pi. But the main difference here is that instead of using sapply as I'm doing here, I'm using instead the mclapply function from the parallel package, okay? Which is the same as an lapply, but the difference is that it will distribute the jobs across a number of cores. Okay? So in this case, what I have here, I have added this extra line here in cores, which is specify how many cores do I want to use. So this is going to effectively split the calculations, which in this case is 1,000 simulations into 4 different threads. It's going to use parallel computing for this. And then once it's done, it unlists this and again returns, prints out the message and returns the file of the data that I just simulated. Okay, that's all that it's doing. But now, since we're using multiple cores, okay, this is not just a single threaded job. We have to specify. We have to tell Slurm that we actually are going to be using multiple CPUs. And how do we do that? Well, we specify this CPUs per task. I think that might be better, right? So in this case, the main difference with the previous bash script is that we now have this new line that is telling Slurm that our job, which is a single task, is going to be using 4 CPUs accordingly to this number. If you have, I don't know, if you're requesting 12, you can replace this with a 12 and then say CPUs per task, 12. And it will run this using 12 CPUs, okay? So once again, I'm here, right? If you take a look at it, cat 02. This is the R script that I'm planning to submit, right? The encores, pi, and everything else, and mclapply, which is like an lapply using parallel computing. And then I have the Slurm the Slurm script right here. And again, to submit it, we just go and do batch. The name of this. Sorry. And that's it. Let me see if I can. No, I did not catch it. I submitted, but the thing is that the job went too fast. It executed, it went in and out right away. And that's it. So, and how do I know that it run? Well, if I list all the files, you can see here. Here we have. This is the file that I asked the R script to save, so it actually executed, and then it generated an output file by default, again using Slurm and then the job ID. So if I print this on screen, it should show me an approximation of pi generated by the simulation, which is what I have here. That's what's printing out. You see? Very simple. Again, the only difference with the previous example was that we have number of cores 4, and then we're using MCL apply, but you have to be explicit to Slurm that you're using 4 CPUs. Okay? Any questions so far?
We have a question from Kai Hong in the chat. If my program does not support multi-threading, can I use multiple cores or nodes?
No, I don't think so, right? Again, so you are responsible for building the parallel computing program. If your program does not allow that, then there's no point on requesting multiple CPUs if your program uses a single thread. But you have to be sure, because, for example, your case, Kai Hong, I noticed that the program that you're using actually uses multi-threaded parallel computing. So, and you have to specify that via command line. So you have to be careful that when you are submitting a job, if your program uses multiple threads, you have to tell that to Slurm, because otherwise, if I believe, I'm not entirely sure about this, but I believe that if you go above the number of resources that you requested, Slurm might kill your job. Okay. Yeah, this is a great question. What's the difference between a multi-node job and a multi-core job? Nodes are CPUs, are computers, right? If I'm talking about a multi-node job, I'm essentially saying that I'm using a job that is using multiple nodes or multiple computers at the same time to like execute. Multi-core is within, it could be just within a single node, your laptop, a single node on HPC, so on and so forth. And you can actually combine both, because you can have multiple nodes at the same time. And within those nodes, you may be using multiple CPUs, multiple cores, right? That's the main difference. Okay. So now the next step is to use multiple nodes. But I'm actually going to skip a little bit this example, because this used to work in the previous version of the HPC cluster. But now in the current version on Kark, it's actually no longer working, because it depends on allowing communication between nodes. Okay, but if you had access to that, and I'm actually, this is a side note, I think I'm going to be requesting for help to the HPC team, so that in the Conti partition and in the Thomas partition and whatever partition we're using at Biostats, we do have access to communication between nodes, so we can use this. Again, this idea is very similar to the previous one, with the difference that I don't know how many, if you guys are familiar with, I don't know if you are familiar with the parallel package itself, but the parallel package has this function that's called make cluster, that allows you to kind of like do what we're doing here, do calculations using multiple computers or multiple cores. By default, when you type make cluster, it will create it will essentially use multiple CPUs within a single computer, right? But I actually have an implementation on the slurmR package that allows you to use multiple nodes at the same time, and it can create a cluster that spans multiple nodes simultaneously. So you can have, I don't know, if you want 100 cores, you can submit things like that. Again, this is not possible right now with the card cluster, but I think I'll have to figure that out with card, so we can make this available for the Conti cluster and the Thomas cluster at least. But long story short, imagine that instead of make Slurm cluster, we're just typing make cluster. So this will work for sure. So we are loading slurmR package, which you can get from CRAN. And I'm creating a cluster object. Here, this is just an example. I'm exporting these variables n and SymPy, so that they are available to all the other computational resources that we are going to be dealing with. And then, similar to the sapply that I ran before, right? Sapply here, that's what we had in the first example. Now we have a par sapply. So this is done in parallel computing. So that's all, and this should work out of the box. Okay, so I'm going to skip this because this won't work right now. Okay, and now this is the example that I think it will benefit most of you, which is using job arrays. Okay, the idea of a job array is that you have a job that you want to replicate across multiple resources. Okay, so for example, in our case, I'm simulating pi, but the pi simulation can actually be parallelized, so it's identical. The only thing that changes is the seed, right? So I need to make sure that I have different seeds, so the random number sequences are independent, right? And the thing is that when you use job arrays in Slurm, within each task of this job array, a special number is generated that goes from 1 to the number of job arrays that you are requesting. So for example, you can have an R script that has something like this. Once it starts, once R starts, you can go and get the environment variable slurm array task ID, which will span from 1 through whatever number of arrays you're requesting. And then do something like, I don't know, if I'm in array 1, do this. If I'm in array 2, do that, so on and so forth. You can do this manually, but I've actually in the slurmR package, which again, so if you want to get it, you can just go and type. Okay, this is taking a little bit. You can just go and type install packages slurmR, and it will get you the slurmR package. Okay. Let me just copy and paste this in the chat. Right there. Okay, so the slurmR package makes this easier. So in this case, for example, again, we do have, it's the same setting as before, but instead of number of cores, this is just changing the name of the variable, so you can understand that it's a little bit different. I'm using number of jobs, okay? So I have the same function that simulates pi here, 1,000 simulations. Each one is going to simulate 10,000 points. This is all what's going on. So then I'm loading the slurmR package, and instead of using sapply, I'm using the function slurm sapply, okay? And what this thing does is that it will take this variable here. It's just like a slurm, just like sapply, but then it will submit a job array to slurm, and it will distribute these calculations, the 1,000 calculations, over 4 jobs, okay? As I mentioned earlier, this is a very low number, but I've dealt with up to 300, up to 500 jobs separately. So if you have, I don't know, say that you have a few thousand data sets that you would like to analyze, you can always say, I don't know, n jobs 200. So this will like distribute your job across 200, your task across 200 jobs, meaning that this won't be happening within the same node, but actually it will span multiple nodes. And all of this is done automatically, which is the key part, right? So instead of you having to deal with all of these of the environment variables, submitting the job array, so on and so forth, the slurmR package does this for you, okay? And the last bit that I wanted to tell you about, this is something that you need to change. The way that this works is it's that it generates a ton of like temp files and things that it will use to submit a job. So you have to specify where do you want to keep all of these temporary files. In my case, I'm going to be using the Scratch file system, my personal folder, meaning that if you try to run this using your account, it will fail because, of course, you don't have access to my Scratch folder. So please change this when you're running this. Okay, and then it will just print out the mean of pi and submit the job. Okay, so let me show you how it's done on HPC. Okay, so again, I have here the slurm apply slurm, right? And this is just like before. And notice here that in this case, we don't need to specify the number of cores because slurmR will do that for you. You don't need to do that. You just need to submit this job, which will be like the main job. And then this function here, slurmR apply, will submit a job array separately. So when I do that, dispatch 04 slurmR apply slurm, it's submitted. Let's see if I can catch it. No, again, it was too quick. The new cluster is super quick to submit a job that I find these guys have done a terrific job. I think it's great. So let's see if it actually works. If I just list out the files that I have here, as you can see here we go. Here's the job that I just submitted, the output file. See, so it saved the RDS file, it did the simulations, and then output this right here. Let's challenge the cluster to see what happens if I request 100 jobs instead, 100 resources instead. So let me edit this. Usually I use Vim to edit stuff on HPC, but some others use Nano, or some others use VI. I don't know. I just like Vim. I'm used to it. Again, so what I'm going to be doing right now is I'm going to change this. So instead of 4, I'm going to request 100. Okay. This is how powerful is slurmR and our cluster actually. Okay. And now I'm going to just dispatch again. 04. Oops. Let's see. There you go. It's working now. See? As before, now this thing distributed the jobs across 100 different tasks. So I'm doing all of this with a single command line here. See? A single command line is requesting 100 let's say CPUs in this case to do these calculations. And now it's done. So if I take a look at this, the output file is here. Let's see how it looks like. Very similar to the previous one, but that's fine. And here we have, right, see? So yeah, so that's any questions so far? That's pretty much like the last example. I have another one, but I can skip that. I want to prioritize questions. Okay. Yeah, so someone is asking if you have to like divide the number of memory, the memory by the number of jobs. The way I do it, I usually use the option that's called mem per CPU, right? So if you are requesting, and it's usually, I don't know, you can say something like like 2 gigs if you're using I don't know, 20 cores. 2 gigs will be 40 gigabytes. You have to just be aware of that, right? Because we don't, again, we do have some large machines, but not all of them are large. Okay, and there's also another option that's called mem, but that specifies memory per node. So maybe that's another way to do it. So instead of you having to do the math, you can say, okay, mem 10 gigabytes. So you're requesting for whatever node you're using, you want to use 10 gigabytes of that node. That's how you do it. Any other question? No? Okay, so let me just show you the last example, which I really like. So this thing of having like 2 files, one R script, and then, I
had a somewhat related question. So you haven't talked at all about the examples haven't actually requested a certain amount of memory.
Right.
Right. So working with very large data, and we already asked the question about the kind of also requesting the right partition to use, but can you, what are maximums on the number of the amount of memory that you can request? And then I guess this mem per CPU how high can that go, I guess?
Yeah, so there's a command here that's called scontrol show config. If you type that on Slurm, it will show you the configuration of the cluster. I've been trying to see if there's any like a memory limits or something, and they don't have, to me, what seems to be like a memory. So for example, if you see default memory per node, they have unlimited. Max memory per node, unlimited. So they have like all these variables here in which they should be specifying limits. I don't think they have specified it, at least not evidently to me. I tried, for example, submitting a job with 40 CPUs in a single node, and they did not allow it. They did not allow it. So I guess that you have to go and try. But usually, the thing is that you just need to be mindful of how much memory your data will be using when you're loading in R, for example.
Right.
And make sure that you're requesting that, because the whole thing of slurmR, of the distribution of jobs, is that they just try to make sure that whatever they throw, whatever resources, whatever node they allocate for you has enough space and CPUs for your task. So if you, for example, you go and your thing uses, I don't know, 200 gigabytes of memory, and then they throw you to a machine that only has 60 gigabytes, then it's your fault, right? It's going to be slow, and it's not going to be working properly. So you have to be mindful of that. Okay.
Great, thanks.
Okay, this last example is for those of you who don't like having multiple files. So as you can see, actually, this what I did, there's another function in Slurm that's called slurmR that's called search Slurm, that allows you to skip writing, having 2 files per thing, right? So in this case, this is just like the first example, I believe, with the main difference that now we have a header here that looks very much like the Slurm bash file, right? So you can see here, once we have this, then you can go and use the search Slurm command. It will take this R script, it will read in this header, write out a bash file for you, and submit the job, all in one step. Right. And furthermore, you can actually do something like this. So again, so we have cut 05. We have this R script that has this header here. And this is something that I'm not going to go into details, but then you can go and make things as easy as instead of like initializing R, you can just go and type slurmR 05 is applied with R. Because the slurmR package has a way to install a command line utility that allows you to submit R scripts directly without having to write the bash file itself. So if I type this, it wrote a bash script for me and submitted the job for me, which I find pretty cool, okay? Because you keep all your setups and everything in a single file. And that's it. So right now, the slurmR package is going to go through an update. I will update it soon, but if you just get the CRAN version, it should work out of the box with the slurmR, with the USC Discovery and Endeavor clusters. Okay. Any question?
Hi, George. I have a question for using slurmR. So we need to wrap all of the codes into a function to use slurmR, right? Mm-hmm. As a parameter of like I don't know. So you just basically wrap all of the codes for analysis into a function and put that function into some supply to do the parallel computing. Is there any other ways like for each in the parallel package to do the same stuff in slurmR?
Yeah. So that's what I was mentioning earlier. So we do have the make slurm cluster function that allows you actually to interact with the for each package. So you can create a cluster object that will span, that could span, I don't know, 100 or hundreds actually of CPUs, and then use the for each package to do calculations together with slurmR. But as of today, the new version of the HPC cluster does not allow to do SSH between jobs. So that's a drawback that forbids slurmR to create these types of clusters. We will change that, so the Conti group and the Thomas group should have that available, I think. So I'll see if that can be done, because that's a really cool thing. I've used that in the past. Again, create a cluster and then use the parallel package or whatever thing that uses clusters to submit jobs in parallel. Does that answer your question?
Yeah, thank you. I'm sorry, George. What is the function you mentioned, that?
It's called make slurm cluster. I'm going to type it in the chat. Make slurm cluster, because it's just like make psoc cluster. It's just like that, but slurm instead.
Got it. Thank you.
Any other question?
George, you have one more question in the chat about dealing with large data sets. Do you need to upload them from your local folder, or can you download directly from AWS?
I think you can download it directly to AWS. I've downloaded large data sets as large as kind of like 50 gigabytes also. I was working with, yeah, I think I downloaded the entire GAU, the gene ontology annotations. So you can download it directly. I don't remember though if I used the transfer node or the discovery node for that, but you can try it out. And I recommend you, if you're going to be doing that, I recommend you using Screen. So take a look at it. The guys are on CART, they tell you about it. So the idea of Screen is that you can initialize like a terminal window that runs in the background, and you can start any command line function there and close that, and you can log out and Screen will continue running. Because if you just go in your computer, log into the cluster and then start downloading things, and if it takes longer than, I don't know, like an hour maybe or less than that, the cluster might kick you out, and you don't want that to happen in the middle of like downloading a big file. So instead use Screen, and once you're within Screen, you can like do whatever you want. If it's going to take hours, then it's fine, because if the cluster kicks you out, the process will be still running using Screen. Any other question?
If not, we should wrap up because we're running a little bit late. Thanks, George. That was great. As George mentioned, we'll be back in about a month to talk about GitHub. But next week, we will return you to your usual programming with the Biostat seminar. So
right.
see you all then, hopefully.
Okay, thank you.
Okay, thank you, George.
Thank you so much.
You're welcome, bye.
Thank you, George.
You're welcome.